Hello. I think it'll be a good time now to talk in more detail about how this CPX decoder ring program, suite of programs, works. Let's look at some pictures here. So you've seen the movie here. That's a recording, a handheld recording, deliberately jerky to test out the stabilization. And that's super fast. You have to be Superman to read that. And then you've seen the decoded version of it that forms the words out of it. All right, a couple of pictures to show you here. Here's just a picture of the Circuit Playground Express with the 2 registration pixels lit and then 2 other ones. It looks like the 1, 2, 4, 8. Looks like this is a 9. Okay, so what happens in the program is we use Open Computer Vision. There's a Python wrapper or layer around that. And the first thing we do is find the bright pixels. And that looks like this. So we load this first image into memory and then call this function, and it gives us a new image with just these bright pixels. And this is just black and white. And this is much easier to analyze. And what the program does is just finds first it finds the registration pixels. So it just does and I'm new to Open Computer Vision, OpenCV, so there almost surely is a better way. But I'm just column by column from right to left finding the places, the columns occupied by these 2 pixels. Then when I have those columns, then I take a scan of, just imagine kind of a thin slice coming down to find where they are on the y-axis. And then what that process ends up with is just the coordinates of the centers of these 2 registration pixels. And now comes another picture. So given these 2 pixels, and knowing that this one is at 0 degrees and this one is at 60 degrees, with a little geometry and some help from some online friends and acquaintances, I've discovered that there's an equilateral triangle here that takes us to the center. And once we have this center, then we can just use cosine and sine to find the coordinates of these pixels on this side. Once we have the registration pixels and we find the origin, find the radius, then just a little bit of trigonometry will help us see if these pixels are on. So that's the way the vision business works. And now let's look at code. The encoder runs on the Circuit Playground Express. And let's just go through it really quickly. This is not so much the focus of this, but we set the pixel overall brightness. We turn off auto write so that we have more control over the way the groups of pixels appear together. We're using this as our white value. We're turning on the registration pixels. And then in our main loop here, we go through the characters of this message and we encode it, turning an A into a 1 and a B into a 2 and a space into a 27. Then we call display, and display goes and for each of the 5 bits, it tests to see if that bit is on. And when you treat this the number as binary, and then it sets the pixel to either white or black. And then it shows the pixels. It shows the 5 pixels. Then we pause for a 50th of a second, and I'm just playing around with this timing. I probably could eliminate this pause altogether because it takes time to turn those pixels on. I don't know if I don't understand electronics and electrons flowing through and why it takes some time for them to sort of warm up. But this is what I've arrived at through experimentation. And then display 0 sets them all to black, and we wait a very brief time. And then after the whole message is sent, we wait 1 second and then we repeat the message. That's the encoder, runs on the Circuit Playground Express. The other program runs on a more powerful computer. And here's the decoder. And as the comment says, it reads a video file, it decodes the message, and it also creates the output file too, the decoded that you saw that's got the words written on it as in the appropriate time points. All right, those bright pixels, let's see if I still have the picture up here. These bright pixels have a value of really close to 255, so they're definitely in this bright area range. That's what this describes. That's how we find those bright pixels. Process video is the main part of the code. I'm just going to close that. Centered frame, centers of frame. This part we won't use. That's kind of for testing. And here's the line of code that calls process video. So let's look at process video now. What does it do? It processes the input video file and writes the results to a new file. And video capture from OpenCV-Python, Python module, creates an object here that we can use to read frames off the video that's stored in this file. And then we read the first frame, and now we have a NumPy array, which is great because NumPy has a lot of really fast, powerful features for dealing with arrays. And we pull the shape out, we get the height and the width of the image. And now we create this video writer to produce the output video. All right, that's that part. We'll scroll down a little bit here. Now, as I showed in the earlier video, the patterns of pixels remain on for several frames. And when they turn on and off, it's not perfect. They may not represent the pattern correctly. And so what we do is we find the largest number that appears there between the blank intervals, between the times when the pixels are dark, off. And this variable will eventually hold the greatest sum of the on powers of 2 pixels. And then message is where we accumulate the message. In video in read, this video capture read gives you not only the frame, but a return code. And that's how you know when you've reached the end. So we have this loop here. Keep going as long as we're getting frames. Now, this is where we create that image with the bright pixels. So at this point, we've got a frame kind of like this, and we want to find the bright pixels. So we call this inRange function. And we give it the range of pixels the pixel intensities that we're interested in. Oh, and I should also mention, we turn it into a grayscale image at this point because the color is not useful to us. And then we instantiate one of our own geometry objects, and I'm going to show you the geometry class in a moment. Okay, now let's come back to, let's see, it's a good way to go through this here, just to see the structure of this main loop here. We find those registration pixels, and if we have them, then we do something. So let's look here. We ask the geometry object to find the registration pixels. Actually, that happens in the constructor. So when we construct the object, it finds the registration pixels, or not. If you give it a bad video, it's not going to find it's not going to find those pixels. But if we do find the pixels, that takes us here. And then we want to find what's on. So on powers, let's look at that now. That's here. And its job is to return those powers of 2 corresponding to the lit pixels. So for this image here, this is the 1 and this is the 8. So that's 2 to the 0 and 1 column, 2, 4, and 8. So 0, 1, 2, 3. That's 2 to the 3rd, 8. So in this case, you'd get a 0 and a 3. So those are the powers of 2 corresponding to the pixels that are lit. And then what we do is take this. This is kind of a, I think, faster way of taking 2 to the power of something. Just taking a 1 and shifting it left. Think of in binary, if you shift something left 1 column, you're doubling it, because each column to the left is double. So what this does is for each of these powers, it produces the value. So we had let's say we had a 0 and 3. 1 shifted over by 0 is a 1, or to put another way, 2 to the 0 power is a 1. So here we have a 1. And then for the 3, well, 2 to the 3rd is 8. So now we have a 1 and an 8. And then the sum function sums those. And then if we're logging, we'll log it out. And if there were lights on, if there was at least one light on, in other words, we're not in the blackout period, then we'll do this. And here's where we're trying to collect the greatest number, the greatest sum of powers. So if we haven't collected it yet, or we have, but this new number is greater, then we'll save this current number into the greatest sum of on powers. Okay, now if it's all black, if the pixels are off, then we have a couple of cases, a couple of possibilities. One is we've already collected something, which is this case. And the other is we're just getting started and we're just going to ignore those frames. So if we've got a greatest sum of on powers, we're going to use it, we'll log it. And then here we do the reverse of what you saw in the encoder. We make a letter or a space out of that number. We print that, and then we add that letter to the message that we're accumulating. Remember up above we have this string called message. Then we reset the greatest sum of on powers to none so that we can start over with another sequence of frames representing one pattern. Then, I don't know if you noticed, the input video was real jerky because I moved it around deliberately, because I have this feature here that stabilizes the image. So this centers the frame and gives us a new image called CF for centered frame. And then we put the text on it with this, and then we write that out. Okay, that is the end of that loop. So let's just do this. That's the end of the loop. Then we kind of close both of those video objects. Great. Let's look at centered frame here. How does that work? Well, it finds how much we have to move the image in order to put the center of the Circuit Playground Express in the center of the picture. And that gives us these delta y and delta x. And then we need to know the dimensions of the frame. Then we set up this transformation matrix. And I'm trying to learn linear algebra. I wouldn't really be able to explain this to you, except that this matrix, when passed to this OpenCV function, warp, and I believe this is pronounced affine, warp affine, will do the translation. And that's what it does. Okay, what's left in this module? Nothing. Now it's time to go and look at the geometry module. Let's see where we first use that. We first use it here. This is where we instantiate our little geometry object from the bright areas. Let's go take a look. This is a module containing the geometry class. It's got some math stuff in it, some typing hints, NumPy, and finds things in the image frames. That's basically what it does. Maybe a little bigger here. Here's the constructor. What do? First, we find the registration pels. IBM years ago, I don't know if they still do, they used pels instead of pixel. Pels is a little shorter, easier to say, easier to type, so call me weird, but I'm going to call them pels in this code. We're going to find the registration pels. So I'm going to press F4 here in IntelliJ IDEA, and that's going to take me there. So we're in the same file, just down a little bit. This is find registration pels. I'm going to collapse this. And what does it do? Well, it gets the bright ranges. I think I talked about this, taking a couple of sort of slices through the black and white file with just the white dots. That's what this does. It gets the, ultimately it produces the centers of the pixels, the pels. I guess we should look at this. It's a little scary. I might not get into all of it. And this certainly could be improved. It could be that all this code could be replaced with just a couple of lines of better OpenCV code. But, all right, so we're starting at the right edge and we're moving left. Just imagine that we're scanning here. So we have a little scanner that takes a whole column at a time and moves from right to left until it finds these things. And this image is a NumPy object, and this wonderful thing here with just a colon and nothing on either side means give me the whole column. It's great. And then along with NumPy any, we can see if any of the pixels in that image are on in that slice. That's really nice. Then there's logic for where are we? Are we in the middle of a range? Are we just getting started? And I think I'm going to kind of gloss over this. This is a generator, so it yields the either left and right or top and bottom. The same function here works for both axes. Okay, I think I'm just going to go with that amount of glossing over the find registration pels. So I'm hiding that, and then I'm going to go back to where we called that, which was up here in the constructor. And we have a tuple of the two coordinate pairs for the registration pels. So we got XY for this, XY for this. Then, if we got the registration pels, we remember the bright areas image, and then we pull out those registration pels into things we call registration pel at 0 degrees and registration pel at 60 degrees. So here's the 0 degrees, here's the 60 degrees one. And then using the Pythagorean theorem, squaring the differences in x and y and summing those and taking the square root of that, that gives us the radius. So now we have the radius. Then we have to figure out the rotation, and the program can handle that just fine. It just has to see what the rotation is. It gets the angle in radians. Just generally speaking, it finds the amount by which the image is rotated. Okay, that's the constructor. And registration pels found is just make sure you have two of those and returns either true or false. Okay, let's look at pel on. That tells you if a particular pixel, a pel for a specific power is on. What's interesting about this? It got a lot of nested functions in here. If I hide some things and we just look at pel on, so we get the pel location, which comes from here, and then we look in the bright areas image at that position and see if there's a pixel on. And if there is, we return true. Otherwise, we return false. Okay, let's see how pel location works. And I'm going to hide this for the moment. It finds the angle based on the power. So let's look at the pictures again. So 0, 30, 60, 90, 120, and so on. So given the power, so for power 0, the angle is 120. That's what this is doing. Tau is the number of radians all the way around a circle. It's 2 pi, according to some mathematicians anyway. And we just multiply starting 12th by 1/12 of a full circle. And then we throw in that global rotation, and that gives us the angle. And then using cosine and sine, we can find the x and y coordinates. So that's the Pell location. We get the x and y coordinates of the pixel at the power we're interested in from here, and return a Boolean whether that Pell is on. Okay, we made it through there. What else? Find center from registration Pells. For this, I'm going to refer you to this answer on Quora. I haven't worked it through. I couldn't say that I completely understand it. But if you read that, it sort of does something like it finds the slope of this line and then uses a fact about perpendicular slopes to find this slope. And I think from there, maybe it finds this point or the radius or something. Anyway, that's that. Okay. We've looked at the geometry class. We've looked at the encode, the decoder class. And we looked at the encoder class. So look at the notes in the video for the location of the code, and maybe this will inspire you to try something. It's been really great fun for me. I'm going to see if I can tweak things a little bit to get it to go really, really fast. See you next time.